Alright, what's up? Welcome back to the channel. This is your boy, the Prokon Geek, and in today's video we're gonna be designing a T-beam. So please stay tuned and let's get right into the content of the video. Alright, but before we actually begin our video, please, if this is your first time coming to my channel, just go up to the top bar. If you're a new visitor, this is my channel, so I cannot subscribe to my own channel, but please just subscribe to the channel. There will be a subscribe button there, so just click on it if you're new, or if you're not new and you've been watching these videos without subscribing, just click on the subscribe button and subscribe to the channel. Also, please leave a like or comment on any one of my videos that I have. I have a Prokon series which I am doing, how to design a double storage, which I have been doing and produce videos almost on a daily. So please subscribe and like the videos so that I keep making them and we keep going with the series. So let's not waste too much time. Let's get right into the design of our T-beam. Alright, now that we are done, let's go back to AutoCAD and also Prokon so that we can now design our beams. So alright, so if you remember what we did in the previous video, we looked at first floor beam 1, which was an L beam, and we designed that in Prokon. So what we are now going to be doing is, I was looking through these beams and thinking which beam should I design, because the previous video was very long. So first floor beam 2 is even way more longer than first floor beam 1 and first floor beam 3 as well. So I was just looking at this and it came to my attention that first floor beam 2 and first floor beam 5 and first floor beam 6, these three are all T-beams. So it's good for us to now design a T-beam, but the best thing is just to single out one so that you have an idea. Then the rest of these you can play around with them on your own, because we do not want to create videos that are too long for the channel and for your attention span as well, because during this lockdown everyone has something to do, so we don't want to keep you attached to the channel that long. So we just want to break down the concepts in very short and concise videos. So what we did, or what I just thought about, is for us to design first floor beam 6. It's a T-beam, it's between, or it's sandwiched, or it is at a continuous edge, so we have a bonus, and that is what we're going to be doing. We're going to be designing first floor beam 6, which is a T-beam as shown with this representation. So now let's get right into how to design that T-beam. Okay, so the first thing that you want to do is, obviously you want to have your Prokon up and open, and then you go to concrete, then you go to continuous beam / slab as usual. I already had mine open. This time we're not going to be using the previous file, we're going to start afresh. So first thing, let's save our file as, and yes, we just went to our working folder. This time it's going to be ffbeam06. Is that correct? We are good. So now we save. Then the next thing you want to do is you want to change your code of practice to whatever country or code that you use. I've just changed mine, so I'm going to click save. And then the next thing we want to go is obviously the first step that we have is the parameters tab. So as you remember, from me, I'm using grade 30 with 19mm aggregate, so 30 is okay. As for steel, I am using 460. For my links, it's 250. Redistribution, I am going with 15. Sorry, that is 250, then 15% is going to go there. Then I'm going with the downward redistribution. Cover the top steel. If you remember from the previous video, it was 45. It was 45. And then dead load factor, this is given as per code. Density of concrete is 24, so we're okay. Percentage of live load that remains permanent, that is okay as well. Then the creep coefficient 2 and 300 to the power of -6, that is okay. Next thing we do is we move into the sections. In this case, we are defining a T section. What is the breadth of the web? The breadth of the web, we still remember, is 230 because we want ours to blend with the walls. Then the depth of our beam is still 300, so we are good to go. Then the breadth of the flange at the top, yes, we have our math sheets, and this time around what we are doing is, if we look at the beam, it has a 6-meter span that is from this point right to this point. which I have indicated. So it's going to be a 6 meter span. Let me just try to annotate it so you see what I am talking about. So this beam obviously spans from there, right, all the way to the end of the balcony, but it in between one of those spans is 6 meters. So that is what we're going to be using. That is the longest span. So for that span, what do we want? We want to find the breadth of the flanges. Okay, so all I need to do is come up with one of my MathCAD sheets, open it up, calculating the flange of the flap. So 6000 is at LX2, so LZ1 is 4, LZ2 is 4.2. Therefore, the breadth of the flange is 650. So we go back to Prokon and we say 650. If I am shouting, please, sorry, we're just trying to make sure this video is as audible as possible. Then what is the height of the flange? You still remember the depth of our slab is 200, so we're good. This is how all of our T-beams will look like in section. So that is the only section we have, and the web is not offset in any way, so we are good to go. That is what we want. Next thing, we're going to go to our spans. In our case, we are lucky we only have 2 spans. The first one is 6 meters, the other one is 2 meters. If you want to verify this, let's go back to AutoCAD. Even you can go to your layouts. As you can see, 6000 by 2000 millimeters, and if you're going back to this case, you can see it's still 6000 and 2000. So for Prokon, what it wants, it needs it in meters, so we just get it in meters, right? So if this is 1 and that is 1, we are good to go. We have defined our spans. And then for supports, obviously support 1, 2, and 3, all of them are going to have columns, but in this case, let's see how our column is going to be oriented. In this case, it's going to be 300 this side, so it's a 230 by 300 if you really look at it. So 230 by 300, then it changes to a 300 by 230, so that is good. So the thing what you're going to do is going to say 230, then 300, then we're going to have 230 as well, then 300, and if you still remember, this is 2.7, this is also 2.7, and this is also 2.7, so we are okay when it comes to that respect. But in the last one, it's supposed to be 300 and 230 if I am not mistaken. Yes, this is how it looks. You see, the last part is the longest side, so that is exactly what you will see when you are in section. When you cut it, when you're seeing it from either side, when you're seeing it going to this side or going to this side, if you're following my mouse. Then the next thing that you're gonna do is, let's also just put it's the same thing. It's going to be the same thing, but the difference is now it's 3 meters. If you still remember from our section, it's 3 meters. If that is what you want to see, this section, it is 3 meters. And now, since we have entered all of these nice, nitty little gritties and we have our spans defined, the next thing we want to do is to define the loads. Okay, so the next thing, after you're done with parameters, sections, spans, supports, the next thing you want to do is put your loads. So that is what we're going to be looking at now. So to put your loads, how many cases do you have? Obviously, you know, you have the dead load and the live load. But in this case now, you have 2 scenarios. When you go to first floor beam 6, this beam has contributions from this panel, which I've shaded as well. As you can see, there is one from this panel. It receives a load, and then it also receives from the panel that is to the left of it. So it receives from both the left and right panel. So the striations represent the beam, right, all the way to its flanges, where its flanges end, where it's represented by the red lines. Then obviously these represent the slabs or the areas contributing to this when it comes to the live load. Otherwise, when it is the dead load, it's both these areas and also the striated area. So now what do? We're going to have 2 dead load cases for each span. So this one is going to have a dead load case contributed by the right panel, and then a dead load case for the left panel. So to do that, let's just go back and start. The first thing we're going to have is the dead load, right, in terms for span 1, but it's going to be a trapezoidal load, so we're going to need 3. So this is how you're going to input these loads. The first thing you're going to have for span 1, then you want for W. For W now, to calculate it, we need to open our sheets. What does it say for dead load? Provide the unit weight of concrete, 24. We're good. The thickness of the slab is not 220, it's actually 200. So we're good. Then measured trapezium height. What is the measured trapezium height? In my case, the measured trapezium height, if I'm looking at it, it is 2,500. I have highlighted it on the screen. So what I'm going to do is I'm going to come there, 2,500. All right. Thus, the theoretical short span is 5 meters. This is for the dead load. Let me recheck to see if that is the measured height. If it is for the dead load, that is not actually the measured trapezoidal height. We need to measure to the of the flanges. So the measured trapezoidal height, please, I'm sorry about that, it's actually 2220. That is for dead load. For dead load, it's 2220. So you put in 2220. The theoretical short span is 4.4 meters. Then the long span from the drawing. What is the long span when you actually measure it from the drawing? With the long span, when you measure from the drawing for this panel, right? Let me just highlight it with a triangle. Let's make sure that it's in what color now. Let's try to put it in red, right? Let's just, I'm sorry about that. Let's put it in red. There you go. Which panel I am talking about? I am talking about this panel which I just highlighted, and I can try and increase its global width so that you guys can have an idea of what I'm trying to say. Right, so this panel that I've just thickened is the panel that we are trying to talk about. So for this one, when it comes to the dead load, we chose 2220. Then theoretically, the long span, the actual long span is, as you can see, 6 meters. And then the actual, the next thing it shows you the short span from the drawing. The actual short span from the drawing is actually 5,000, which is 5 meters. So we are okay, and we have put that in the drawing. Then the span coefficient, this is how it's going to be defined. 6,000 divided by 5,000 LX. LX means the short span actual, then LX is just the short span theoretical. So this is what happens. Our load factors, that's equal to QD is given by gamma multiplied by T. Therefore, the Q for the dead load is 4.8 kilonewtons per square meter. Therefore, the actual dead load weight, which is being transmitted to the beams, is going to be QD multiplied by LX over 3 multiplied by 1 minus 1 over 3 K squared, where LXA is responsible for K squared. So in that case, we get WD 5.46 kilonewtons, and this is what we come in to say. So it obviously starts from 0, then it goes all the way to 5.46 kilonewtons. So where does it start? This is what happens. Let's go. It starts at 0. This is 0. Then it goes all the way to 5.46 kilonewtons at this point. And that point is, let us now measure how, what is the distance from x is equal to 0. That point is at a distance of 1.445. So this is what we're going to say. In Prokon, it's at a distance of from 0 to 1.445. This is what happens. It starts at 0, then goes all the way to 5.46, as you can see on the drawing, to at 1.445. It is 5.46. Then what happens is it remains as 5.46, right, from 1.445, and for a distance of how much? So this is what I'm trying to say. It goes all the way to 5.446, then remains as 5.446 for all this, for a distance. Now let's measure the distance. What I'm going to do, I'm just going to say continued. For a distance of 2055. 2055. So this is it. It remains for a distance of 2.055. That is the point. So it remains as 5.46 for a distance of 2.0455 from the point 1.445. Now, it starts off at 5.46 kilonewtons per meter, which is which point? Which is this point now. The point I am just putting, see where my mouse is hovering. This is the point where it starts off at 5.446. And that point is a total distance of, let's measure it. 3490. Actually, I think I am snapping to something that is not correctly correct. Let's, yes, it is a miss a little bit. Right, sorry about that. We just want to make sure we snap into the correct point so that we measure the correct distance. I think I missed it by a bit of 10, so it is a distance of 3,500. So it starts off at 3.500, so 3.5. Then the other thing you want to notice is that if you add 1.445 plus 2.055, it's going to give you 3,500. To just verify that, let's just go the 1.445 plus 2.055. Let's just verify it. It's 3.5. So that's the other thing, cool trick you want to do. The value that you put for A is equal to this previous value plus this value. I hope you understand. It's that's the thing, that's the trick. So next time, what you want to do now, what is the distance when it finally goes there? It goes for a distance of what? It's going to move, it's going to go to 0 for a distance of, let's see, we'd actually measure that distance 2.500. So that is okay. That is what we're going to put here. We're going to put 2,500, and at that point it will be 0. As you can see now on the screen, it is clearly drawn the same thing as we are seeing on our diagram. So this is what you do for the first dead load case when it is trapezoidal load. Okay, so since we have been dealing with which panel is this? We have been dealing with the right panel. We now need to deal with the left panel. Or what we can do is we can finish with the right panel, but now let's go to the live load component. So what we're gonna do is put live. We still would span 1. Since it's a trapezoidal, you're gonna put 3, right? So how does it start? Obviously, it starts off at 0. Right, when it is at this point. Which point is it? This is the point that I am talking about. It starts off at 0, but then it goes all the way up. But I think you're going to find that it is symmetrical. Let us just see. Let us see. It's 2, 2, 0. Are you sure that I snapped to the correct points the previous time? I just want to be sure I snapped to the correct points, and also that I snapped to the correct points in the previous video, because it's not really supposed to be different. It's supposed to be symmetrical. Next thing I could have done is missed the 20, but it seems I snapped to the correct points. I just want to be sure that I snapped to the correct points, or I could have taken the flanges, but I think it's okay. Let's just use what we have on the screen right now. It's 2,200. But no, we're still doing the live load for this right panel, so please forgive me for going to the left panel. Let's finish up with the right panel. So with the right panel, now we want to use the live load. So to do the live load, so that we just use the sheet once and then we use it the other time for the next time. So what you're going to do is you're going to calculate the live load second. That is what you calculate second. So the measured trapezium height for the live load, in this case, when you're measuring it for the live load, you measure from this edge to where your trapezium is, and for the live load, the edge is 2,500. So this is what you're going to do. You're just going to say 2,500. There you go. And then obviously you saw where we got 5, and in this case WL, that is W for live load, becomes 6.404. This is what you do. What you're going to do now is it's 6.404. obviously. So I think you already know it's going to be similar to the above. This is how you enter when it's a trapezoidal load, and then there you go to 0. But then the distances, what does it say? The distances are the same. If you want, you can double check in AutoCAD, but the distances are the same. And remember, your live load should be a bit of a similar to your dead load. In this case, as you can see, it's ending there. This is how it starts and this is how it goes. If you want, let me show you. Because remember, the same area is what contributes to the dead load and the live load, except now you know for the dead load the height is measured up to the flange, whilst for the live load is measured up to the center of the beam. Okay, so this is the two scenarios for the right panel. Next thing that we need to do is now we need to do it for the left panel, and we're still at span 1. So yes, it can be a bit tedious, but then just go with the flow. Let's see. I think I'm putting too much. This is too much. We need 3 only. So this is okay. Now, in essence, it should have been a mirror image. The issue was us just going to copy, but since it's not a mirror image, let's just go and put in the values. In this case, it's 2200. So what I am going to do is, let me go back In this case, it's no longer, it's now 2200. So what I'm going to do, let me just delete 2200. That is the only change we're going to have. And this time it comes to 5.41. So this is 5.41. So it's 0, then 5.41 there. Then you want to copy this, paste it there, paste it there, paste it there, and then it is 0. But the distances now are a mirror image, so that one at least you can copy and just paste it there. The reason why I'm saying that is, let me see if you want, let's just verify it so that you are satisfied it is a mirror image. So we're going to dimension linear. Let's just get it from there. Right, I am snapping to something that is wrong. Something is happening. Yes, as I told you, I am snapping to something wrong. It is supposed to be a mirror image. I don't know why my snaps are not working as supposedly, but let me just show you. Hopefully this time we snapped the correct position. As you can see, it's a mirror image. 1445, 1445, then 2055, and then 2500. So that is what we're going to do. So now let's just we go back to Prokon. Our distances are the same. We put that for the same as well. Then the next thing that we are going to do is copy these distances since they are the same for the live load as well. Then we paste them there. But this time around, we want to calculate for the live load. And in our case, let's go back to AutoCAD. The distance is already there. That's why I was saying 220 is supposed to be equal to 2200, but then I'm not sure what happened for me there. So 2000 is 2500, 2500, 2500. So the live load remains the same as 6.404. So it's 0, then 6.404. And then you're going to copy that C, Control V, Control V. As you can see, it's sort of doubling your loads, and then this goes to 0. And then as you can see, you have inputted the loads for the first span. You've taken care of both the left and right panel of your slab. That is to say, you have put the loads that are coming from this side and then the ones that are coming from the left side. The next thing now we need to do is put the loads for the next panel, that is the 2 meter span, and deal with this span and then this span of your slab. So let's do that right now. Okay, so now we are moving on to span 2. So to move on to span 2, as you already know, you can go back to your Prokon. This time you're going to put the dead load. We're going to start with the right span, the right panel, if you remember. So this is going to be 1, 1, and 1. Then obviously the live load is going to have 1, 2, 3. Remember, that's the rule of thumb when you have a trapezoidal load. But in this case, wait, do we have a trapezoidal load? Because I'm not sure. No, we now have a triangular load, so we go back to 2. But then I've just showed you how to do trapezoidal loads. So as you can see, trapezoidal loads can be a pain in the donkey. The pain in the donkey. In this case, we're now doing span 2. So this is span 2 and span 2. So we are now reverting to which method sheet we're now doing this slab distribution to beams if it is triangular. So obviously the first thing you want to do is the unit weight of the concrete, 24 kilonewtons per cubic meter. You're okay. T is 200. We're okay. What is the measured triangle height? Since we're dealing for self weight, we need to measure the smaller height, which is 990. So that comes down to, let's see, 990. That's okay. Then the short span length is calculated for you automatically. It's 1.98. QD is 4.8, therefore WD is 3.168. So what we're gonna have is, it's obviously gonna start at 0, then it's gonna go all the way to 3.168, then it's gonna go from 3.168 all the way back to 0. Okay, to 0. This is going to start off at 0, but then let's see the distances. It obviously starts off at 0 because this is where it is 0, and then it goes all the way. What is the distance from this? It's 1270. Okay, that is nice. 1270, and I'm sure that then the remainder of that distance will have to be 730. Yes, it is 730. So it starts off at 0, then goes for a distance of, let's see, 3.168. Start off as 0. This is 1.270. This is where you put 1.270. Then this First time it starts off at 1.270, then goes for a distance of 0.73, and as you can see, voila, there is your load. You've actually inputted it into Prokon and you're good to go. So if you see, if I remove 0. This, it looks funny, but or even you can just remove it like this. It looks funny, but then when you start it like this, there you go. Then when you put 730, this is how it looks. Then the next thing that you want to do is you want to do it for the live load. Then for the live load, what does it say? What is the measured triangle height? The measured triangle height is 1270. 1270. So let's go. What is the measured triangle height? We just want to put it right. 1270. So that's 4.233. So that is what you want to put. You want to put, this is obviously 0, then it's 4.233. Then you want to copy that same load, then put it there. And this time it's going to be 0. This is from where? This is from, it has the same values as your dead load, so this is how it would look. It has to be similar, so as you can see, when you put it, the live load is similar to your dead load in shape. That means you're doing it correctly. Now, since you've put for the right panel, we need to take into account the left panel as well. So this is going to be the live, and this is going to be for the left panel, then the left panel. So for the left panel, in our case, let us see it as a perfect mirror image of the right one. So we don't have to stress ourselves. It is as easy as going to, where does 2 start? This is where 2 starts. Copying everything like this. Right. Oh, I'm sorry about that. Let's copy everything. Control C, Control V. There you go. There you have your load has increased. That is as perfect as it can be, which is the beauty when you have symmetry. If you do not have symmetry, you need to do it all over again and make sure that you're doing it correctly. All right, so this is how you put in your loads when you have your symmetry. And I think we've discussed the T beams and also the Flange beams, so this is okay. Once you measure it, you've put in your loads correctly and you've interpreted your diagrams nicely. Next thing, we don't have any wind load, so next thing, let's view our results. All right, now that we are done with the loads, the next thing is to view the results. And let's see, go to view, and let's see our elastic deflections. Short term, we have 5.952. We're good. We don't have any problem there. Then, oh my god, it is 24.63. So I know some scrupulous engineers will be like, okay, that is not too much. That is just 4.63 millimeters. Dude, that is not what we do when we're doing with the Prokon Geek. We do things professionally. So once you have a problem like this, it's obviously 4 millimeters, 0.60. The best thing that you want to do is just come back to your sections and increase the depth of your beam. So the overall depth, in this case, I'm going to increase it by the thickness of one brick. So let me put it to 375 so that it kind of blends. So all they have to do is just remove one course of a brick and just increase it with the concrete of the beam. So it's now 375. So the depth goes from, it was what? It was 100 to 175. So let me I just put, okay, sorry about that. What the hell am I doing? 375. So it's a brick. So now let's go to the view. Our loads are still the same. Go back to your view and voila, there you go. Your short term has decreased to 3.85 and your deflection has decreased to 19.06 by just removing one layer of bricks and putting concrete. So you're 19.06. So you're good to go. You don't have any problems. Then the moments on the shear, there is your moment. It's 88. It's not too much. Then your shear is not too much as well. It's very little. So I think we have satisfied our beam when it comes to deflection. The moments as well are good. For the steel, yes, as you can see, we don't need too much steel. This is minimal. This is very little steel that we need. So let's go to the output file, crack file. We talked about this. We don't need to worry about this. The next thing we need to talk about is reinforcing. So what are we going to do? Maximum bar length. We're going to change this to 6. And then the maximum or minimum diameter bar that we want, we're just going to change this to 25. Let me put 20 so I don't want anything that goes above 20. Then the minimum diameter for the length is okay. Then the maximum I want is 12s. Shape chord 72, I'm okay. Then the first bar mark, we're just going to change this to 1, and everything else is okay. And then we are going to put click generate reinforcing. So there we go. What do we have? We have 3 y12s at the top, okay, and then 2 y12s here. What, this is not too good for me, but what I'll do is 3 y12s. Let me just push it back. This is what the most important thing that we need to note is the amount of steel. It's negative 804.22 square meters at 6 meters, which is this top. This is going to be Hogan steel. So this is the steel that you need. So we have seen the steel that is needed. We would play around with this detailing when we now go to pads, but at least we have an idea of the steel that we need. So this one actually needs Y20s. So you are seeing 20s at the bottom. And then in this place, I think I'm going to put 2 Y20s when you actually come to the detailing, the actual detailing codes, or we can use 2 20s and 1 12, because the detailing says if your beam is not more than certain width, you should not put more than 4 bars or what. So Prokon, as you can see, it's already putting 5 bars there. It's 3 Y12s plus 2 Y12s, which is just too much bars. The poker will not be able to go through these bars and vibrate your beam, or poke your beam, or vibrate your concrete. So those are some of the things we are going to talk when it comes to detailing. We're going to change these bars when it's in pads. It's much easier than changing them here, but you can always try and change them here. So what I'll try and see is, let me see, 3 y12s. Where are my y12s? All right, so this is what I'm going to do. I'm going to put 1 y20 there. All right. And then there's a y12s. What I'm going to do is I'm going to put them as 16s. And voila, you see our steel is adequate enough. As you can see there, it's over. And one glitch I've seen about Prokon is this area at the end, usually your blue line or your red line starts a little bit lower than the blue line. But the most important thing is to check whether where it starts peaking is higher than your blue line. If it is higher than your blue line, you're good to go. So this is what we're going to do. This is the main reinforcement. We're going to just offset this to Prokon, but this one is too many bars. I'm telling you, these are too many bars. We don't need this too many bars. So what I'm just going to do is 2 y12s. Let me see, 1 y16. There's 1 y16 somewhere. I don't need this bar mark 4 to be. I'm just going to put it as 1. Then we're just going to put it as a 20. And as you can see, we have more than enough steel at the bottom. So we now have 3 bars at the bottom. So we are okay. What's the other thing? I'm going to refine this when it comes to Prokon, so don't worry about that. We're going to do that in pads. I'm going to show you how to refine these bars and detail these beams. So the other thing that you want to do is just change maybe the names here so that when they go to your portion, they are okay. So section 1 and then obviously section 2. So what I'm going to do is I'm going to put, these are stirrup, for me, I call them stirrups 1 and stirrups 2. And then, oh, sorry, it's a different, this is clip 1. This is supposed to be clip 1. Then this one is going to be stirrup 2. Let me delete that and put 2. And this is going to be clip 2. Alright, so we're good to go. Shape code 35, shape code 35, send it to. Then the next thing, shear reinforcement. We already have a diagram of what the shear reinforcement needs to look like. If I look at this, what I can do is let me just push it there. Okay, that is just a little bit too much, so I think it's okay. This arrangement is okay with me. Every line in blue is taken care of. So the next thing, sections. Do I need to add extra sections? Yes, let me just add an extra section. Let me put my B there. Then I'm going to add section C, D, and E. So this is E. So what I'm going to do is I'm going to put it in 1, then I'm going to put it at 5 meters. Alright, that's okay. Then the other thing is I'm going to put this at 2, then I'm going to put it at 0.5. Alright, that is too much, and let me just shift it there. Then I'm going to put this at section 2, then I'm going to put it at 1.5. That is good. These are the sections I need. Then as for 3D view, this is a view of how it will look like in 3D. As you can see, there is your T-beam. That is how it is represented. And as you can see, when you're seeing it on the side, this is where I was saying we need to change some of the bars so that we don't have 4 bars, we only have 3 bars. So those are some of the detailing parameters we're going to change when it comes to using pads. I find it difficult to do it under this tab, so it's not good for everyone when you're doing pads as well, and it also will help you how to use pads, so that is the good thing. So this is the 3D view. Then for the bending schedule, all you have to do is FF beam 06. It's okay. First grid line is what? Now the first grid line letter, is it going to be A? It's no longer A because this one is at grid C, but it will be 1, 2, and 3. So that is what you're going to do. So you're going to change this from A, and you're going to put 1. First span 1, 2, 3, and everything else is okay. Change this to A4 and click generate your schedule. Just wait for it. Okay, this is, can we just wait for it for a bit? All right, there you go. There's your bending schedule. We're going to have to change this in Pro, but let me just show you what it will look like so that you guys have an idea of what we're going to be changing when it comes to detailing in pads. So once your schedule has been generated, this is what it will come up looking like. This will show you the bars, the sections as well, which we have added, and obviously the bending schedule, as you can see where my mouse is playing. So what we're going to do is, in the detailing part, we're going to be changing these bars, changing their lengths, using the detailing parameters that are recommended by SANS. So don't worry about that. We are going to get to that section. So this is it for today, ladies and gentlemen. Please remember, if this is your first time coming to the channel, click on the subscribe button. If it is your 30th time you're watching these videos without subscribing, please just subscribe to the channel, leave a comment, click the like button, smash the like button, and also let's just get this thing started. And I think the next time we're now going to the slab because we don't want to waste too much time. I think you now have an appreciation of how to design beams. If you still have anything that you want, leave it in the comment box, and then I will dwell on it on another video. So thank you very much for tuning in. Until next time, see you.